Okay, good morning to all of you. So I hope the screen is visible, right?
Yes.
Yeah, okay. Yeah, so right. So today I'm going to start, in the previous class we discussed DES, data encryption algorithm, that is a private key or symmetric key encryption. Today I want to give one public key encryption. So public key encryption is also called asymmetric key encryption, right? In public key encryption, each entity here means say the person or a computer or whatever, each entity A, okay, so each entity A has a public key and a private key. So public key is public, everyone knows it. Private key is secret and it is kept with A. The task of computing D given E is computationally infeasible. So there are some hard problems. So computing E from D from E is equivalent to solving those hard problems. So, but right now for them, there are no vulnerability algorithms to do those. Okay. So to understand these things, public key crypto system, we need to start with an example, right? So I will start with an example. Yeah. So that things becomes easy. So the first one is that RSA public crypto system. I hope none of you took this topic. So that's why I'm taking this. So RSA public key encryption. Yeah, so this is actually given by 3 persons. So R means this R Rivest. Yeah, and S means A Shamir. And this A means Edelman. Okay. So these 3 people gave this algorithm. That's why RSA, right? Yeah. So this is a public key crypto system, right? So actually, public key crypto systems encryptions, mainly 3 things will be there. Okay, in fact 4. The first one is that key generation. Key generation. Next one is key distribution. Key distribution. The next one is, so key generation, key distribution, encryption, and then decryption. Then decryption, right? These are the 4 items are there for the any public key crypto system or asymmetric crypto system, right? So now I'm going to tell in RSA how it goes, right? This first of all, RSA depends upon factoring. N is difficult. Factoring problem is difficult. It depends upon that. Okay, but anyhow, so let me first state it. So key generation first. So I'm giving different algorithms. First one is related to key generation, right? Till now, any questions? Anything you want to ask? Okay, no question. Fine. So let me write an algorithm so it will be clear to you. So this is algorithm for key generation. Of course, it also includes distribution. Distribution is not much here. That's why algorithm for key generation. Yeah. So there are first what we do is that okay, let me write a summary how it goes, right? Summary goes like this. Each entity creates an RSA public key, and a corresponding private key. And a corresponding private key. This is a summary. So how do it goes? Each entity, again, entity means a person or a computer, whatever. Okay. Each entity A should do the following. So those who are only attending today, also no problem. It is completely new topic and you can understand easily, right? So what they will do, first they do the following. First they generate two large random primes. Generate two large random distinct primes. Distinct primes P and Q. So I hope my writing is okay. Is it?
Yes,
Each roughly of same size. Each roughly of same size means a number of digits you can say of same size. Okay. First they generate to A, the entity A. The entity A choose two large primes. Okay. So P and Q. Then he or she compute N is equal to P into Q. Right. N is equal to PQ and automatically, you know, phi of N. What is phi of N for this? You remember? Can you say what is phi of N? Yes, any one of you?
P minus 1
Phi
into
of-
Q minus 1.
Yeah, so this is phi of P into phi of Q, right? Phi is a multiplicative function, so it is phi of P into phi of Q, but phi of P is P minus 1. So this is P minus 1 into Q minus 1. Now select a random integer. Select a random integer E. So where E lies in between, so 1 less than E less than Euler phi function phi of N, right? Such that GCD of E comma phi of N is equal to 1. Okay, you know what happens when E comma phi of N GCD 1, that means E belong to UN. Yeah, you know UN, right? We studied in the number theory UN. E belong to UN. That means that it has a UN is a group with respect to multiplication. So E has a multiplicative inverse, right? These things you know. So then by Euclidean algorithm, so by Bezold's identity or Euclidean algorithm, so people generally write Euclidean algorithm only. They will not say Bezold's identity and all. Yeah, Euclidean algorithm by Euclidean. There exists D belongs to, I am writing UN, you know already. So that E into D is congruent to 1 modulo phi of N, right? This much is okay. Yeah, what is the thing? Two primes we took P and Q, N equal to PQ and phi of N we computed. So these are all doing by this one person A. A is doing all these things, right? Yeah. Oh, sorry, some problem came. So 1 minute. Yeah, okay. Yeah, okay, sorry. Some problem coming. Right. Okay, all of them are there. Okay. So we are going to have this part. Is it visible? This?
Yes, sir.
Yeah, okay, thank you. So by Euclidean algorithm, there exists d says that E into D equal to 1 modulo Phi n, correct? Yeah, right. So now, once we have these things, now we can say that, so clearly this here 1 is less than D is less than Phi of n, right? And ED equal to 1 modulo Phi n, right? Now by fifth property, now A's public key is, A's public key is these n comma e. That means this n and e known to everyone, and the private key is d. D is the private key. Of course, people say that p and q also. He will not reveal p and q. He or she will not reveal p and q. Some people say that p and q also private key, but that is not required. D is the private key. These three. So this is the key generation. And the distribution also, because this is, he will now distribute. Public key means distributed. He announced it. N comma E is my public key, and so private key anyhow we will not tell to anyone. Any questions here? Key generation. So he will take two big primes of equal size and computes their product n. Now once you know n, it is difficult to find p and q. Factoring problem is difficult. Okay. So you do not know P and Q, computing phi of n is also difficult from n. Are you following that? You know n, then you cannot find a phi of n unless until you know that factorization of n. Computation of phi of n is also difficult. Okay. Then once we know n and phi n, right? So are you following? So even though I give n, you cannot compute phi of n. Okay. Phi of n is not known to the person, any person. Yeah. So select a random integer e and which has a inverse, multiplicative inverse, that is d. Now n comma e is the public key and the private key is this one. So any doubts? Can I proceed? Suresh ji, is it everything fine till now?
Yes, sir.
Okay, good. Nothing actually, very simple. Now we are going to do that. Yeah, now we are going to tell you the encryption mechanism, right? What is the encryption mechanism, right? So now, so small thing here, definition. These have some names actually, not required that much. This E is called encryption exponent. Encryption exponent. Yeah, this D is called decryption exponent. Okay, and N is called modulus. Okay, so I'm not written as like a definition, but so the integer C and D in RSA crypto system are like that, it is there, but we are already in RSA. So this is called encryption exponent, decryption exponent, and N is the modulus, right? These are clear. Now coming to algorithm, this particular algorithm. So RSA public key encryption. So algorithm RSA public key encryption. RSA public key encryption. So how it goes? Okay. So Somoy, are you here? Subhamoy? Yeah. Okay. Good. So easy actually. So easy to follow. So summary. Now B want to encrypt. B encrypts message M for A. Yeah. So B want to send some message M to A. What he will do. Okay. So first to encryption, right? Then decryption. So encryption, how it goes, right? So obtain A's. So obtain A's public key. What is public key of A's? What is that?
N,
N, E. Okay. So it is known. Okay. So this is a small a, right? Now B. So he takes that. Then he took message M. Generally, message is also number from 0 to n minus 1. Yeah. So he took the message M in the interval 0 to n minus 1. And then C, he computes. He computes ciphertext. How he'll compute? C is equal to M power E modulo N. So he know N, he know E. M is a cipher. M is the plain text want to send. Okay, M is the message. B wants to send to A. Then what is the ciphertext? So the C is called ciphertext. So it is equal to M power A mod N. Yeah. So now we got the ciphertext. What next he will do? He sends C to A. So with this encryption is done. Is any questions here? The simple one, very simple to understand this particular public key crypto system. Yeah. Now the next one is decryption. Decryption. In the decryption, so what is the goal actually? So goal is that to recover M from C, right? To recover M from C. So A should do the following. A should do the following. What is that A will do now? Somebody can guess? Yeah. If you already know, you can tell, no problem. So he has to use his private key right now. Decryption.
C power D.
Yeah. Yes, please.
C power D.
C power D. Correct. A's private key. So private key D. Right. Now C is known to A, not M. So what A will do? So C power D he will do modulo N. Yeah. So this is going to be M. Why? That is a question, but he will compute and he will get M. So with this entire thing is done. Okay. So this is key generation and this is encryption mechanism. So any doubts? So Kanak, is everything clear till now?
Yes.
Yeah. Okay. So simple, not complicated. Right. So why this is working? So let us have that particular aspect. So let us see the proof that why this why C power D now becomes M, right? So some of you already know, but I'm just telling you. So we have that since ED is congruent to 1 modulo phi n, right? Yeah, ED is congruent to 1 modulo phi n. So then what happens that? So there exists K. So that means phi of n divides ED minus 1. There exists K belong to Z such that ED minus 1 is equal to K times phi of n, correct? This part is okay, no problems, right? Now, now it is easy to see that generally we choose M such that, so case 1, case 2 we can take up. So GCD of M comma P, okay, otherwise you know why, since you've done the course in number 3, you know very much well. So no need to tell all these things. So you know that P is a prime number. Since P is prime, right? Right. Then you know this part, M power P minus 1, right? M power P minus M power ED. Okay, so first of all, M power P minus 1 is M power P is congruent to, right? M power P is congruent to M modulo P. Otherwise, I will go by Fermat's little theorem. Yeah, I'll go one after the another. Okay. Since P is prime, if M comma P GCD is equal to 1, then what is that we have? Then M power P minus 1 is congruent to 1 modulo P. This part you are clear with, right? Then what is going to happen? Now it is easy to see that here you know that this Phi n you know, right? Phi n is P minus 1 into Q minus 1, right? Right. So now what is my ED actually from this? So from this, ED is equal to 1 plus K times phi of n, right? Yeah. Now what is going to happen to this? So P minus 1 times K times this into Q minus 1, that is my phi of n, right? So plus 1 is congruent to what? Hello? Easy? Tell me fast, we'll go.
M.
Yeah, this is M, right? So modulo P. Any questions here? See, if M comma P GCD is not 1, that implies what? What is M comma P GCD now? P is a prime number. So M comma P GCD becomes P, right? That means this implies that P divides M. In this case, in that case also, this is true, correct? M power K times P minus 1 into Q minus 1 plus 1 is congruent to M mod P is true even in that case. Are you okay? P divides this, P divides M, P divides M, right? P divides M, then it is true. Be quick, you know number theory part. These parts are very clear to you. Can I proceed? Is it okay? Mehak, is it okay? Fine.
Yes, sir.
Yeah. So what is that we have that what is this K times P minus 1 into Q minus 1 plus 1? What is this quantity? What is K times P minus 1 into Q minus ED, right? So M power ED is congruent to M modulo P. This is what we got. Yeah. Yeah. Any question, please? Somebody is talking. I'm unable to listen. Increase your voice. Okay. Yeah. So then no questions. So I am proceeding. So very simple that yeah, we have M power ED equal to congruent to M mod P. Can you guess what next we are going to prove? Yes. I am giving hint. Similarly. Yes. Yes, please fast.
Same thing for Q.
So m power ed is congruent to m modulo q. Also same logic, right? Now m comma q gcd is 1. Now p comma q, sorry, p comma q gcd is 1. So p comma q gcd 1. So p divides m power ed minus m. Q divides m power ed minus m. So you know that p comma q gcd 1, then what is going to happen? So p into q divides m power ed minus m. So this implies m power ed is congruent to m modulo n. That is m power e power d is congruent to m modulo n. That is c power d is congruent to m modulo n, right? That is the logic. So decryption is working. C power d, if I do, I am getting m. Okay, so I'm getting m. Any questions here? I think very straightforward, simple observations. Euler's theorem we are using, right? We know that or Fermat's little theorem direct, or you can use directly Euler phi function. M power phi of n is congruent to that, also you can use. But I'm brought from Fermat's little theorem, but you can directly brought from Euler's theorem also. That also you know. So I hope this is not much a difficult part. So am I done? Is it okay for you? So I'll go, Achila. How is that everything till now? Fine.
Yes, sir.
Yeah.
Understood.
Yeah. So just I'll go a little fast now. So RSA public key system. First one is key generation. Key generation, each entity, each person, okay, so has a public key and private key. How they generate? So for example, some person A want to share the key. So how he generates key? So first he choose two big prime numbers of equal same size. So compute n equal to p into q. So phi of n equal to p minus 1 into q minus 1. Then e is a number relatively prime to phi n. So now you know that there is a inverse for it, right? Now the public key is n comma e and private key is b. Okay. Now coming to the encryption scheme. Now b want to send some message m to a. Then b collects public key, a's public key n comma e, and message m from 0 to n minus 1. Okay. Then compute c is equal to m power e. That is a ciphertext, and sends c to a. Then how decryption works? M is equal to c power d mod n. Why this is giving c power d m? So proof is given here. Yeah, any questions you can ask me. Okay. There are many attacks are there on this one also, but even then by choosing this p, q and n, by choosing p and q, we can make this is very effective. So that's why still RSA crypto system works. But you want to know those, what are those? So I will give few of them, right? So one of the first thing is this part. Few things I'm telling you one after another. So for example, RSA has multiplicative properties. Yeah, any questions? Yeah, RSA has multiplicative property. What is that one? So multiplicative property means that so you have so C1 is a ciphertext corresponding to M1. C2 is ciphertext corresponding to M2. So can you tell me what is a ciphertext corresponding to M1, M2? So this is a question. Okay, what is this quantity, right? So that is the question. So it is easy to observe that. So for that, let us consider this, right? M1 into M2 power C power E. Okay, what is this equal to? It is equal to M1 power E into M2 power E, correct? Now, this is congruent to what? Modulo N. We done these in the modulus, right?
C1, C2.
Yeah, this is C1 into C2. The beauty is this part, okay? So that means that M1, M2, so ciphertext corresponding to this is C1, C2. So if I know for C1 and I know ciphertext, I know the plain text for C1, I know plain text for C2, and I know plain text for C1, C2 also. Is it okay? Yes?
Yes, sir.
Yeah. Right. So that is a good, nice thing about this one. So this is called, this type of encryptions are called homeomorphic encryptions. Homomorphisms. This is the first time I observed that. I'm very happy by looking this part, because homeomorphisms, the property used in the actually in day-to-day our life. Yeah. So this is called homomorphic property. So RSA is a homomorphic encryption. Why this is useful? Can somebody help me? If you have any. Yeah, otherwise I'll tell. Yeah, I'll tell now. See, you know Dropbox. Yeah, anyone of you know Dropbox? No one knows. Okay, Kanak, where you use, where you store your files in the online?
Google Drive.
Google Drive. Okay, now Google Drive, but earlier people use it to put, even Google Drive is one thing, or Dropbox. There are many online activities are there that you can store your information there, right? Yeah. Okay. Now you sent your message M. You are storing M1. Where you are storing? In Google Drive, right? But how it is stored? Is it stored as M1? No, it is stored as C1, so that other person cannot get it. Otherwise, you give some information, right? You give link or something. Huh? So similarly, M2. But you want to do something to this C1, C2, right? So now getting back and all, instead of that, so now you are doing here itself. Okay. So yeah, that is advantage, that homomorphic encryption. So without actually getting back to M1, M2, directly we are doing. Yeah, C1 into C2, M1, M2 ka text is actually C1, C2. I simply multiply there itself. I'll get the, that is the ciphertext for M1, M2, right? So getting your original text and again multiplying them, instead of that, directly I can multiply C1, C2. That is a, so like that, certain operations without getting back and forth, I can do there itself. Yeah, so this is a very advantage for the homomorphic encryptions. So there are many variants of this fully homomorphic encryptions like that. So that is a further nice things to read. Those who are interested in cryptography, we will discuss if you are interested more about them. Yeah. So this is a nice property, but there is a disadvantage of this. Okay, now I want to talk about that. Any questions? Is it clear? So C1 is a, M1 is a plain text for C1, M2 is a plain text for C2. These are the ciphertexts. Then C1, C2 ciphertext ka plain text hoga M1, M2, right? So this is very much clear. Yeah. Right. Now how this is used actually? You remember that chosen ciphertext technique? You remember? Chosen ciphertext attack. Do you remember that? Any one of you? Ciphertext only attack is different. Chosen ciphertext attack. That means, see, you have Alice and Bob, and we have eavesdropper, right? So he's adversary, right? So, for example, they are A and B are very confident that even I will give what Alice will do. Sorry, this eavesdropper. Eavesdropper will give some plain text. Yeah, eavesdropper gives some plain text. Chosen plain text. 1 minute. What is it I'm talking about? Yeah. So you can you recall what is it? Chosen plain ciphertext attack. Yeah. Hello. Yeah. So actually, chosen ciphertext means he gives some ciphertext to A, right? Now A decrypts. So A decrypts the ciphertext C M and gives M to E. Now what is that E has now? So C comma M, one pair E has. Who is given the ciphertext? Eve. Eve give to A. A is confident that I will give one ciphertext ka plain text, still he cannot get it the original text. Okay. So yeah. So is it okay? This part is clear. Chosen ciphertext is that this my crypto system is so strong that even so eavesdropper gives some ciphertext and A gives a main plain text corresponding to that pair E has. Even then, now we will say A send some some B send some message to A. Eavesdropper get the ciphertext, but even with this information, he cannot get the ciphertext, plain text. That then it is called very good system. Otherwise, it is attacked by chosen plain ciphertext attack. Is it okay or not okay? Tell me, then I can explain further. So, Amia, is it okay? Hello, are you there?
M is the plain text, right?
Which one is plain text?
M.
M is the plain text corresponding to C.
And
See,
if you give M to E, then that defeats the whole purpose, right?
no, not this M. This is a separate. See, E gives some ciphertext to A, not
Okay. I understood that.
other
Yeah.
ciphertext. Some other. Yeah, some other ciphertext C to A. A decrypts is okay. Let us say C tilde, okay, and M tilde, right? Yeah. So this is not original plain, whatever going on. So now E has this information as well as now, for example, now new conversation is going on between A and A, right? See, generally, so A thinks that my system is very perfect. That's why he gave extra powers to E. Even then he cannot do it. Then it is a good crypto system, right? In general, passive attacker does not ask for these questions. Simply, whenever he see the ciphertext between A and B, he'll try to get the M. But now we are giving more powers to E. Even then he cannot get. Then the ciphertext is become strong. Are you okay?
Yes, sir.
Yeah. So now how it goes? Now let us see in this particular case. Okay. So for example, suppose that I'm giving you that adversary. Suppose now it will be clear to you. I'm much more explanation I'm giving. Suppose so active I'll say, right, active adversary So active adversary wishes to decrypt. Wishes to decrypt what? Decrypt ciphertext, right? Decrypt the ciphertext. C is equal to m power e mod n. So you want to decrypt this, right? So intended for A. So B is sending C to A. Sorry. Yeah. So this is the goal. But now what? Suppose that A also decrypt. Suppose A also decrypt arbitrary ciphertext for the adversary. Are you following this thought? Arbitrary ciphertext to the adversary, right? And so other than C itself, okay? Other than C itself. Yeah, I hope this part is now clear, right? Okay. So now the adversary is very powerful, very intelligent person. The adversary can conceal C by selecting so random integer x belong to un. Un means units, right? By selecting x belong to un, what he will do, he or she will do. Okay, so computes C bar is equal to x into C into x power e mod n. Okay, so now this e gives C bar to A to decrypt, right? So then how do A decrypt this part? Are you okay? I'm telling you one more time. So B is sending some message to A. So let us say M. So how we'll send? So ciphertext is C, M power E. E wants to know what is this M. Okay, but suppose that A also decrypt arbitrary ciphertext for adversary other than the C itself. So A told that I can do decrypt one ciphertext for you. Then adversary is intelligent. He can choose this one. C bar is equal to C into x power E. What is C? I think you are not there. I think C is the ciphertext. B is sending to A, right? And that A can E can get, right? And X is chosen by him or her. And E also known publicly, N also known publicly. So C into x power E computed. That is called C bar, right? Yeah. So now C bar is some plain some ciphertext. Now E gives the C bar to A to decrypt. Okay. What A will do now? That is the question I'm asking. Can you explain me that?
Can you repeat the question?
Yes. Yes.
Can you repeat the question?
See, E giving some ciphertext to A to decrypt, right? So E gave C bar to A. Now to decrypt, what is that A gives to E? This is the ciphertext. Decrypt.
We'll give C bar power D.
So he will give M bar. What is M bar? C bar power D modulo N, right? This is given. Given to whom? E. But what is M bar? M bar is C bar ka plain text. C bar is a ciphertext. So A promised that I will give one plain text to whatever the ciphertext you give me. So he chooses the ciphertext very nicely. How he chooses the ciphertext? So now they are communicating. He waited for some time. Whenever they are started communicating, then he took that C first, okay, and he took arbitrary X belong to but UN. It has a multiplicative inverse. Then E and N are known publicly. So he computed a C into X power E, that is C bar. Now you promised me that I'll give a ciphertext, you give me the plain text. And now I'm giving you. C bar is given to A. So asked him to decrypt. So he gave M bar, right? Back to E. Now what is that E? Now E knows. E knows this pair, C bar and M bar, right? Now the question, can E get C now? Can E gets C now? M. Yeah, this is the question, right? Okay, so let us compute. What is M bar you told? Hello?
C bar power
C
D.
bar to the power D.
C power D, right. But it's C bar is what?
X power E into C.
Yeah, X into C power E, right? So X into C power E power D. Yeah, sorry. X into C power E power D.
X power E into C.
X power E into C, yeah? No, I don't think, okay, let me see. Yeah, sorry. C into X power E, okay, sorry. X power E into C power D, okay, fine, yeah. What is now happening? So this is X power E power D, right? So C power D modulo N I will do. What is I'm going to get?
C power D.
No. I'm doing modulo N.
X power ED will be 1.
Is it 1 or X?
Oh, sorry, X.
Why it is X? Can you tell me?
Because X power ED will be congruent to.
So
So
we took,
that
yeah.
again the same expression as before.
So this is C power, but C power D modulo N is M, right? So M modulo N. Now what is that he has? Now he has this relation also. M bar is congruent to X M modulo N. Now what is that he knows? He knows M bar. He knows X also. Can he get M now? That is the question, correct? So can you tell me what is M now? M is congruent to, yes, M bar.
Our X power ED minus A.
Yeah, right. So he will get M now easily from this. So it is actually called adaptive so chosen ciphertext. So he's adapted the situation very nicely. That's why it is called adaptive chosen ciphertext attack. Any questions you want to ask me? I've done nothing actually. I'm telling you that So eavesdropper give an extra power that you can challenging. There is a challenge that okay, I can give one plain text, whatever the ciphertext you choose. So that challenge they gave. Then he used very nicely. How he used? So he chose C into x power e, where x is arbitrary integer in UN. Such that x has inverse. So he chose the C bar and he gave C bar to A to T grip. So he got M bar plain text. So now he has C bar M bar, right? So now can I get M now with this? Okay. So that is the idea. So M bar actually C bar power D, but C bar is x power C into D, x power C e power D into C power. So this x into M mod N. So then I'll get M from this. Is it okay?
Yes, sir.
Yeah. But of course, we can have some techniques actually. I'm not going further all this. So I'm just giving you that this type of attack is possible, right? So it is so chosen ciphertext attack is possible for RSA crypto system, right? So it defeats that. But can I do some changes to this? Even chosen ciphertext also will defeat. Yes, it is possible. So I'm not going into all those details right now. So I want to give one glimpse of certain things. Okay, what do you mean by crypto analysis? This is one of the things. Okay, now I'll tell you more other things, but instead of going more into this part. Yeah. So can I proceed?
Yes, sir.
Yeah. Okay. So another one is that, for example, I'm telling you that suppose we suppose somehow D is known. Okay, let me write in other color. I'll take this one. Now suppose that D is known. Known means known to opponent. Now the question is that suppose D is known. Is it possible to find N? Is it possible to find factors of N, right? Finding N is not actually, N is already public. So factors P and Q, is it possible? What is advantage if I know P and Q? I know everything, right? Yeah, D, once D is known, I can get everything. But this is a number theoretic problem. Suppose मैंने आपको D दिया है, then can you find factors of N? This is the question. Is the question clear?
Yes, sir.
Yeah, question is clear. Good, thanks. Yeah, so now try to look into that part, right? Suppose that you know this part, okay? We have one thing, okay? Remember that ED is congruent to 1 modulo phi of n, correct? We have this thing with us. So from this, what we can have, ED minus 1 is equal to some k into phi of n. I already used it, but I'm telling one more time. Yeah. So now, if suppose a comma n GCD is equal to 1. From that, what happens? You know that Euler theorem, a power phi of n is congruent to 1 modulo n, right? So from this, what going to happen? A power ED minus 1 is congruent to 1 modulo n. This is not a problem. Sorry. Hope, is it clear? Right? Yeah, this much is okay. So now I take that my ED minus 1 is equal to some 2 power s into t. it is okay. I can take some even part into odd part. Okay. So where t is odd, right? This much is fine, right? So then it is easy to show that. So there exists A belongs to UN, right? Such that A power 2 power s minus 1 into t is not congruent to 2 plus or minus 1 modulo n. In fact, we can find half of them. Is it clear or not clear? What is if I square it? Hello? So you can check this. At least half of them will not satisfy. That means at least one UN, one A will be there such that A power 2 power s minus 1 into t is not congruent to plus or minus 1 modulo n. So if not, you can take it as an exercise and try this. Once this happens, then automatically for such A, okay, GCD of A power 2 power s minus 1 times t, yeah, minus 1 comma n is not equal to 1. So that means that we got a non-trivial factor. Yeah, this is the main crux actually, exercise problem. So is it okay?
Yes, sir.
Yeah, so once we have this, so now what is that? We have one factor, can we get another factor? Obviously, right? N is product of only two prime factors. In fact, so randomly we can choose A, at least in 2 steps on an average, you will get the, we can get the factor of N. Okay, so this establishes the following thing. So yeah, finding D is equivalent to factoring N. Yeah, finding D is equivalent to factoring N. These are two equivalent. See, once I know factoring, I know the P and Q, then I know D, obviously, right? If I know D now, I proved that how to factor N also, right? So finding, so but factoring N is a difficult problem. So finding D is also a difficult problem. That's why this system is difficult. This is another thing I want to convey. Yeah. So another aspect now I want to say to you. For example, we are using the same E, another criterion. Yeah. So if you want, you can take small break now. So let me
So are you saying something? You are mute.
Yeah. So yeah, sorry. Now get back. Now let us have some examples so that things will becomes easy for us. Let us take two primes P and Q is equal to 2551. Yeah, see these two primes of equal size almost, right? So my N is equal to now P into Q, right? So this is equal to, so it comes like this. Okay, and you know phi of N also, that is equal to, you can compute to this P minus 1 into Q minus 1. Yes, right. Now you have to choose E. So let us choose E is equal to some 367 4911. Okay, some big number, but it is less than phi of N, right? And relatively prime to phi of N. Now we need to see that it is E congruent to 1 modulo N, right? Phi of N, modulo phi of N, right? Yeah. So that we can figure out that this D is equal to, this D is equal to, so 422191. Okay. Now what is a public key? So public key is, so this N comma E, right? So N is given here and E is given here, and the private key is this D, right? So for example, now encryption, how it goes, right? For example, my M is equal to, so it is between 0 to N minus 1. So my M value is equal to, so 5234673, some number is there. So now how to compute? C is equal to M power E, right? M power E mod N. Okay. So this is going to be some number like this. Okay. Modulo N I'm doing. So 3650502, right? Yeah. Now, so ciphertext is this. Now decryption. This is encryption. So in the decryption, what we're going to have, that C power D modulo N value, right? Which is equal to, so we'll again get back the original message. Okay. So M. So easy to check these things, not complicated. So one example we have. And now I'm going to tell you one thing that, for example, you know that when E is small, then it is easy for us to encryption, right? But be careful. I am giving one example. So for example, three people choose N1 and N2 and N3. Okay. So B wants to send a message to these people, right? But for all three have same E. E is equal to 3 only. Is it clear what I'm saying? These are modulus, right? Monlo, there are three modulus, N1, N2, N3, and E is the 3 comma N1 GCD1, 3 comma N2 GCD1, 3 comma N3 GCD1, and they choose the public key as E equal to 3. 3 is common, but N1, N2, N3 may be different. Okay. Now B want to send a message. Suppose same message he want to send, then what happens? That is the question. Suppose B wants to send same message M2 these people A1, A2, A3, right? Then can you tell me what is C1 value? Hello? A1 public key is N1 comma E. A2 public key is N2 comma E. A3 public key is N3 comma E. So B want to send a message M to A1, A2, A3. So what is C1 value? I'm not asking tough question. Be quick actually. Yes, please. Am I audible? Oh, Mehak, can you tell me what is C1? Achila, what is the problem? You tell me, then I'll explain. Hello?
Yes, sir.
Yeah. C1 equal to? No. How you are computing ciphertext? Plain text and we are doing something, right?
M to the power E.
M to the power E. But what is E now in this case? So I'm telling you that for A1 public key is N1 comma E, N2 comma E,
So
N3.
M to the power E mod N1.
Yeah. So under E equal to 3 is given, small exponent. Yeah. So it is M power
M cube mod N1.
N1, right? So C2 is congruent to M cube mod N2, right? And C3 is equal to M cube mod N3. Okay. Suppose that N1 comma N2 GCD1. Okay. N2 comma N3 GCD1, like that. A भी assume कर लो, right? N2 comma N3 GCD is 1. Okay. N1 comma N3 GCD1. Okay. So can I get now? So now there is a person, right? E. Yeah. So there is an adversary always, right? Adversary checks. Adversary now has what is the information adversary has? Adversary has C1, C2, C3. So can he get M now? Can E gets M? That is a question mark. See, B is sending message to A1, A2, A3. But the same message, that is the thing I want to say. And also exponent equal to 3, right? So ciphertext is M cube, C2 is M3, and C3 is M power 3, mod N1, N2, N3, right? Now can I get M? What is M actually? M is lies in between. You know that M is less than N1, right? M is less than N2. M is less than N3, right? So can you say what you can say about M cube then? It is less than N1 into N2 into N3. I'm giving all the details. So now you can guess easily what is that I'm looking for. Where you come across this type of thing. GCD1 and so equations like this. So
Chinese remainder theorem.
Chinese remainder theorem, right? So now by Chinese remainder theorem, right? So I can find a solution. There exists a unique solution. Modulo N1 into N2 into N3, correct? What is that value? Okay, so that is my X. Suppose X is solution, so X is equal to M power 3 only. Okay, are you following? Okay, it is a reverse direction actually. X is congruent to C1 mod N1, right? X is congruent to C2 mod N2, right? I know C1, C2, C3. Now X is congruent to C3 mod N3. Yeah, I have these things. I want to find a solution X to this, right? Now you understand Chinese remainder theorem. Without this, you told, thanks for that. I want to find X. Now what is X? X equal to M3 only, M power 3, right? So now how to compute m now? So x power 1 by 3 will give m. Is it okay? Are you okay?
Yes, sir.
Yeah. So I'm telling you that certain occasions we can get the message easily. Okay. We should be careful. Even RSA crypto system, there are some many advantages, but we need to be careful when it fails. Okay. Like that, there are many other occasions. So that is a nice area to explore, but I will not go into all the details now. Instead, otherwise you will be a little painful. You are already listening me for the longer time. So now instead I will go to other systems, right? So other crypto system which is also based on a factoring of integer. Okay, that I will tell you now, right? Yeah, be ready. Yeah, so this is called Rabin public crypto system, right? Rabin public key crypto system. Yeah, but it is also depends upon the same. Yeah, so here what is the key generation, what are the things and all I'll tell you. Okay, so first key generation. So key generation goes like this. Again, uh, two large primes generate two large primes P and Q. Okay. Second point is that compute again same n equal to P into Q. Third part is that A's public key is n and the private key is P and Q. Pair P comma Q. Any questions here? Nothing, right? Yeah, this is key generation. Nothing again, same as that one, but it is much simpler than that. There I had to compute phi of n and E, D, all that. Here only n is the public key and the private keys are P and Q, right? Now what is the algorithm? Encryption now. Encryption algorithm. Yeah, okay. Encryption algorithm goes like this. So B want to send some message, right? M to A. Then obviously the step one is that she chooses the public key, A's public key. That is N. So next B. So once we know that, so we'll choose M. This M belongs to 0 to 0, 1 to up to N minus 1. Right? So C. C is that so computation now. C is equal to M square modulo N. Very simple. Now only M square. Okay. D sends C to A. Is it clear? Now no E, no D, anything. Just simply M square only. Okay. What is a decryption algorithm? So decryption, right? I'll write here below. Decryption algorithm. So decryption algorithm goes like this. So there are 4 values M1, M2, M3, M4. 4 possible square roots. Okay, this is the number 1. Number 2 is that so the message sent was either M1 or M2 or M3 or M4. So in the elementary number theory button book, there is a area called coin exchange, coin problem, right? Coin flip problem. There also this is discussed if you want, right? A somehow, I'll tell you how somehow also. A somehow decides which of these is M. Yeah, but finding M1, M2, M3, M4 depends upon P and Q also. But the only problem here is that out of these M1, M2, M3, M4, which one is the correct? That is a small problem here. Yeah, but computing M1, M2, M3, M4 depends upon P and Q. But P and Q known only to A, right? So he can compute. But now the problem comes that how do you check which one of them is the actual correct message? Right? For example, other people also able to compute M1, M2, M3, M4, at least 1/4 they are correct answer they are having, right? Yeah. Yeah. Is it okay? And I want to tell you how this can computed, but is the key generation and encryption is clear? Decryption is clear?
Yes.
Yeah. So the key generation is that take 2 big primes and public key is N and private key is PQ. Encryption algorithm is that take M square, that's send the matter. Not much. Rabin public crypto system is simple. But only thing is decryption is little complicated here. So how we'll get M1, M2, M3, M4, and also how do you choose M in from these M1, M2, M3, M4? These are the 2 points I need to discuss with you. But there are many algorithms. So there are number theory, lot of number theory involved here. But I will give you some algorithm how to compute M1, M2, M3, M4 once we know P and Q. Okay, so I'll give the algorithm. So checking that algorithm is true, again, we need to discuss more. Yeah. So algorithm I am telling you now, right? Okay. So what is that we have? So first P comma Q GCD is 1, right? This implies that there exist A comma B, right? There exist two integers, right? A comma B belong to Z such that AP plus BQ is equal to 1. So fix these, fix A and B. Why I'm writing fix A and B? Do you know why? Also, P is congruent to 3 modulo 4 usually, and Q is also congruent to 3 modulo 4. Yeah, so in this particular algorithm, because these are not unique, right? You know that Bezos identity is not unique. So for example, I say 2 comma 3 GCD is 1. Now 2x plus 3y is equal to 1. So what are these x and y? They are not unique. We can find many, right? Oh, I hope it is clear to you.
Yes.
Yeah. So that's why you are fixing now. So you know the P and Q GCD1. So there exist A and B that we know by Bezos identity. So then I'm fixing A and B in this algorithm, right? Okay. Once you fix that, okay, then compute. This is step 1. Step 1. Fix A and B. Now step 2. Step 2 is that So step 2, what we will compute? We'll compute R is congruent to C power P plus 1 by 4 modulo P. Yeah. Since P is congruent to 3 modulo 4, so P plus 1 is divisible by 4. So I'll compute this. I compute R value. Because C we know. Then we'll compute S. So it is also similar to that. Yeah. Mod Q. So no problems. Very easy to remember. Yeah. R and S we computed. Then we compute X and Y. So X is congruent to APS plus BQR. Do not ask me why this. Okay, we can explain, but that takes time. I'll tell you why I'm doing all these things also. If you give me 1 minute. So then it is the same again. Very nice to remember these things. APS minus BQR. So interesting thing is that what are A and B? You know. What is C? You know. What are P and Q? You know. Now, once you have R and S, then I'm computing X and Y. That also very simple. APS plus BQR, APS minus BQR, right? So S is coming from Q, R is coming from P, but the S is multiplied to P and R is multiplied to Q part. Yeah. So now, once we have this, we computed these 4, then the square roots of C modulo N are X comma minus X, Y comma minus Y. Okay. I cannot give the proof for this now, but this is one assumption we are assuming now. So otherwise you can check. Actually, Burton number theory book may be high, but anyhow you also can try. If I start giving proof, it takes more time. Is it okay? This algorithm will give you, these are the square roots of C. What are the square roots of C? What is C? C equal to M square. If square root of this is M, but these are M1, M2, M3, M4. 4 will be there. Yeah. So you know how to compute M1, M2, M3, M4 now?
Yes, sir.
With this assumption? Yeah. Okay. Now, but the problem now, second problem is there, right? How to, now I'll choose one of them, right? So for that, there is a redundancy. We'll add more bits to it. Okay. So if you add more, okay. So just let me write and then I'll give one example so that it becomes easy for you. Okay. So what we can do is that, so we'll by adding, we will add a pre-specified redundancy. Pre-specified redundancy to original plain text prior to encryption. Before encrypting, I will add some redundancy to the plain text, pre-specified redundancy. So then it is easy for me to figure out exactly which one is the M out of M1, M2, M3, M4. So now right time to give an example so that things becomes easy for you, right? So let us have an example. So now my values are, I'm taking P is equal to 277 and Q is equal to 331. Okay, these two big primes I took. Now N is equal to P into Q. So this is equal to this number. Okay, I have N with me. Okay, Now, for example, I have my m is equal to, this is my plain text. Okay. So that is 100 1111 001. Okay. So what is that we are doing is that B replicates the last 6 bits. The last 6 bits. So these last 6 bits, okay, replicates to, okay, to get ember. Okay. So, okay, I'm calling this as ember so that m is now becomes different. Now my m is equal to, what is my m? So I will repeat the last, right? 10041 but I am now repeating last these parts, right? This part. So 111001. This is my m. This is binary. This is binary. Now it's a decimal. It's a decimal value. Okay. It's a decimal value now becoming 40569. Okay. It is decimal representation, decimal value. Now this is my m. Okay. Now what is that B will do? So what is B is doing before actually sending the message? This is my original message, but I convert into M by repeating the last 6 digits. Then she is computing the ciphertext. So C is congruent to M square modulo N, correct? So what is that? So my M is equal to this number 40569 square modulo N. N is 91687. Okay. If I compute, I'm going to get 62111. Right. Now, this is the thing. Then what is going to happen is that, so when I square, I'll find the square roots by my earlier technique. I'll get 4 values, right? So I'll get 4 values. That is 69654. Yeah. 22033. 40599. 40569. Sir. Means xx minus xy minus y, you understand, right? But modulo we are doing, that's why all are positive. Now what we will do, we will convert them into binary. So exactly one of them will fits to my ember, my m. Okay. So I'm not writing what are these binaries here. So that's not going to make sense to you also. But you will see that only one of them will matches with this bigger one. Okay. Is it okay? Or do you want me to write that? So I just write one. M1 is going to be like this. M1 is equal to, right, 10001. I don't know how many zeros are there. So sorry, I'm not going to write that. So then you can check that one of them will only match. This is the theory we need to establish if you want. So is the Rabin method is clear?
Yes, sir.
Yeah, nothing actually, very simple. The only thing is that to get exact one, we have to do some pre-specified redundancy we need to do. With that idea, we can work out. Now, the remaining time, I will tell you another crypto system that is related to digital logarithm, discrete logarithmic problem. Yeah, so take a small gap. So I will start in 2 minutes, right? Yeah. Okay. So any questions till now? Right. So this is a new one. With that, I will start today. But very simple. So each entity creates public and corresponding private key. As usual, I am not writing that part. So, but here, so the step one is that not two primes and all. Okay, only one prime now. Okay. So generate a large random prime p. Okay, one prime will take, and a generator alpha for ZP star. What is ZP star? You know, right? So I'm calling as UP, but you know that it is a 0 to p minus 1, right? Not 0 is removed, 1 to p minus 1, right? And we know that it's cyclic group. We know that it has a primitive root, right? For modulo p, we discussed these things. So it has a generator. Primitive root exists for primes, right? Yeah, that I'm taking alpha, right? Luckily, we done number theory, so now things are becoming easy for us, and we are seeing the applications now. Okay, so select a random integer. Select a random integer. Are you all of you here? I hope. Please concentrate. Very important. Easy. Select a random integer a. Okay, where 1 less than or equal to a less than or equal to p minus 2. Yeah. In fact, we will not take a equal to 1 also. P minus 1 is minus 1. So generally we'll avoid them. Right? Yeah. So random integer like this. Okay. And we'll compute alpha power a. Right. Now what are the public key? Now key generation part. Okay. This is key generation, right? Yeah. This particular thing what I'm doing is called key generation. So you can stop here and you can use for the key exchange problem also, right? Yeah. Okay. Now that is a public key and what is private key, right? Public key is public key and private key. Sorry, public key. What is public key? Okay, I'll write like this: key, public key, and private key. Public key is P is a public, prime is public, alpha is public. What is alpha? Yes. What is alpha?
Generator.
Alpha is generator for the group ZP star, and alpha power A is also public. Okay. Now what is private? Private is only one thing, that is A. Okay. Only A is the private. So now I gave you P, I gave you alpha generator, I gave you some element, but difficult to find A. What is this telling? So ZP star is a cyclic group. So it has a generator alpha. So every element is expressed as alpha power A, but I give element A, then finding exponent is difficult. That is discrete logarithm problem, right? Yeah. So more clarity will give Mehak will give later. So this is a tough problem, finding A from alpha power A. Yeah. So that is the idea ElGamal people used. Okay. So even though Diffie-Hellman gave this, but they are unable to give the crypto system from this. To give crypto system, what is that we need? Trapdoor information, right? So we need to have a public private key. With that, I can get the entire secret, right? So we need to create like that. Okay. So this much is okay. But now actually ElGamal crypto system comes, right? What is algorithm? How we do encryption and decryption, right? Now algorithm for encryption and decryption, right? Yeah. What that B will do now? B want to send a message M to A. Wants to send message M to A. This is the goal, right? What she will do. Okay. As usual, what is the first step? Obtains A's public key. First he will look A's public key. What is A's public key? Recall. Okay, every time. What is A's public key?
P alpha and alpha to the power.
Power A. Yeah, like that. You revise things, it becomes easy for us, right? Now you take a M. M belong to ZP star, right? And C. That means from automatically M comma P GCD is 1. Okay. So select a random integer K. Select a random integer K. Who is selecting? Who is selecting?
B.
B is selecting, right? Even A also does not know. Okay, think of all these things. Okay, then it becomes easy. Okay, so how we'll select again 1 to P minus 2, right? Then next one, so computation. What is now B has? B has a public key information, that is P alpha power A. M also know message want to send. This is another thing. She knows. He or she knows. And another random generator K. Now by using all these things, he will compute. He or she will compute something, right? So what is she will compute? She compute gamma first. So gamma is equal to, right? Gamma is equal to alpha power K modulo P. Alpha power K modulo P. Is it okay? Is it possible to compute? Yeah, I know alpha, I know K, I know P. So I'll compute it, right? What else I'll compute? Second part. We'll compute delta. So what is delta? Delta is congruent to, now till now a message is not came into picture, right? Now we are using. And also I'm not used alpha power A, I'm using it now. Alpha power A power K modulo P. Are you okay? Are you fine? Yeah.
Yes.
So what is he sent now? What is the ciphertext, right? Now last step now, ciphertext. Send the ciphertext. This is beautiful. In here, ciphertext is not one; it is a pair now. Ciphertext C is equal to gamma comma delta. It is a pair now to A. But A goal is to get M only, right? Not gamma delta, all these, right? Right. But also A does not have K. In spite of that, how do A will get now M? That is the beautiful part. These are very, very nice things actually. Now decryption. Now you know how to encrypt. So encrypt is clear to all of you. So message M, arbitrary random integer K, gamma and delta computed. Gamma is alpha power K, delta is M into alpha power A power K. Yeah. So sending the ciphertext gamma comma delta to A. Okay, good, very nice. Now decryption, right? So decryption is simply that. So now, of course, A use is private key. A use. What is private key? Do you remember?
A.
A, very good. A is the private key, right? What is A again? A is randomly chosen integer from 1 to P minus 2, like K. A is chosen by A, but K is chosen by B. Okay, good. Now she computes gamma power P minus 1 minus A, but this is equal to what? You know that part. It is equal to gamma power minus A only, right? Gamma power P minus 1 is 1 gamma. Yeah, so you can easily do this. It's not a problem. So otherwise directly compute gamma power minus A if you want. Okay, but gamma power minus a is what? What is gamma? You forget. What is gamma?
alpha power k mod p.
Alpha power k only. Alpha power k. Modulo p always be there continuously. Luckily only one prime, so alpha power k, but power minus a. So it is equal to alpha power minus ka mod p. Right? You understand why minus ka we need actually? You remember? Delta p I have alpha power ak. Now I have alpha power minus ka. Right? So that k, I do not, a does not need k. That is the beauty of this. Is it not not good? Alpha power k, I do not need k now, but gamma value is alpha power k. So I am doing minus a, and here alpha power a pe alpha power a is given, but no one knows a. Okay, only entire alpha power a is known. Now a knows a, so he is using power minus a, he done, right? Gamma power minus a, he done. That becomes alpha power ka. But how do you get m now? Can you guess? M equal to what? No, you have to come up.
Delta into alpha minus k.
Yeah, but that is gamma power minus a. All these things you can worry about. So it is simply gamma power minus a into, you are correct, into delta modulo p, right? See the beauty here. So if I multiply this with gamma power minus a, so this gets cancelled, I'll get m, right? Simple. Yeah. So but a without a we cannot get it, but finding a is difficult by discrete logarithmic problem. That's why decryption is very nicely done. And so yeah, this is the approach. I don't think it is a difficult for you to understand that why this is equal to this. You already understood. So do you want some example? So just I'll give a little faster. So take p is equal to some 2357 again. Nice prime number, product consecutive prime numbers, right? 2357, and alpha is equal to 2 is a generator for this Z star 2357, right? So alpha is this. Alpha is a generator, right? Now a is equal to 1751. So arbitrarily chosen by a. It is chosen by a, right? Now decryption, right? So m is equal to message m is equal to, so b wants to send this 2035. Okay. So now what is that b will do? Yeah, can you tell me? Choose random k. Okay, so k is equal to, she chooses 1520, right? Yeah. So what next she will do? She will compute gamma and compute delta. What is gamma? Gamma is equal to alpha power k, right? So that is 2 power 1520 modulo 2357. Okay. So gamma is going to be 1430. Okay. How delta is computed? First m we had to take, m is coming here into, yes, alpha power a. What is alpha power a value? That we need to compute, correct? So alpha power a, which is equal to 1185. Yeah, we'll compute that. So now this is alpha power a 1185. What is that I have to do? Delta value, alpha power a
To the power k.
power k again, right? So power k is 1520 modulo p, that is 2357, correct? Yeah, so this is going to be 697. Okay, I have gamma delta. What is the public key now? What is that she will send? B sends this 1430, comma 697 to A. Yeah. Now A computes. So how AM will be getting? Will get. So so we need to compute gamma power minus A, right? So first A computes gamma power minus A. Means otherwise gamma inverse of whatever, gamma power minus A. So this is equal to, but why I'm writing instead of this P minus that one, you remember? Why I'm writing P minus 1 minus A? So P minus 1 is actually, now it becomes a positive integer actually, right? No need of negative and all, that's nothing actually, okay? So this is equal to 872, right? This is same as gamma of minus A only. This P minus 1 is order of the group, right? So this is gamma power P minus 1 into gamma power minus A. But gamma power P minus 1 is 1. Order of the group is P minus 1. So nothing is there, okay? Yeah, so now M is equal to what? 872 into, yeah, 697.
6.7.
Yeah, good. So mod this one, mod P. Yeah, I'm not writing P here, which is equal to 2035. So we'll get the message back, 2035. Yeah, so I hope it is clear to you. I'll stop now.